Okay, hi everyone. Thank you for joining us today. Very excited that you're here. If you're watching on YouTube, we'd love to have you hit the subscribe button to stay current on what we're doing. If you have a talk or speaker suggestion, you can go to our public GitHub repo, which is github.com/protocol/research, and open an issue. There's a template provided where you can make a request or a suggestion for a talk or a speaker. Lastly, we'd also love to have you join our mailing list. You can sign up for quarterly newsletters and/or future talk announcements, funding opportunities, that sort of thing. You can do this in the footer at research.protocol.ai. All that said, let me go ahead and introduce our speaker today. Dr. Stefanie Roos is an assistant professor for distributed systems at TU Delft and the Delft Blockchain Lab. Her work deals with trade-offs between privacy, security, and performance in decentralized systems. She contributed to the censorship-resistant peer-to-peer network Freenet and designed Speedy Murmurs, a routing algorithm for payment channel networks like Lightning. Her current research is focused on improving layer 2 protocols for blockchains, as well as designing more efficient anonymity systems. And also just a note that the co-author for the paper that Stefanie will be discussing, Kristina Hostekova, is also on this call and will likely be chiming in. So with that, I will turn it over and let you take it away from here, Stefanie.
Hey, thanks for having me, and welcome to my talk. So today we're going to talk about a very recent work I had with Lisa, Sebastian, and as already mentioned, Kristina from TU Darmstadt, which improved routing protocols for payment channel networks by allowing splitting and what we call interdimensional routing, which you will see in a couple of slides what it actually means. And it's really fresh work. It's under submission at CCS, and we're supposed to hear back from it like today if it got accepted. So we're very excited about it. We're thinking it's really good. And with this, I'm going to go into the actual topic. So one note, I'm probably going to be a bit fast on the blockchain background, because I assume that most of the viewers here are familiar with blockchain. If I'm wrong on something and assuming knowledge that you don't actually have, just let me know and then I can add some details on the fly. So, okay, first slide. Okay, good. Oh yeah, right. Jonathan asked me to add the research series first slide, and I forgot to remove my original first slide. So that's the same thing again, but now first slide. A short recap on what channels are. So for most of the time in this paper, we're going to talk about payment channels, but it also applies to state channels, which are a bit more general. So what is a payment channel? The idea here is that you have an underlying blockchain, but the blockchain is most likely pretty slow. So your transaction take a lot of time to be confirmed. It's not very scalable, doesn't manage that many transactions and so on. So channels are one way to overcome a lot of these issues. And the key idea is that if you have someone with whom you want to do a lot of transactions, a friend whom you tend to give money, borrow money from and then pay it back and so on, the local supermarket, people with whom you do a lot of transactions, then at some point you can just use the blockchain to make a deposit. So we're having the parties A and B, and both of them are locking funds, in this case, X coins and Y coins, on the blockchain that are specific for their trading with the other party. And once this is done, you no longer need the blockchain as long as everything works out. So we have this initial state where A can send up to X coins to B, and B can send up to Y coins to A. Now if A sends something, for example, Z coins, the balance on the one side decreases, and on the other side, it might increase. It depends a bit on the type of the network. Sometimes it does not. In this example, we're saying that the coins will remain in the channel by being added to the balance of the other party. Then A can do that again, and potentially B can send something, and this is all without any fees, and it doesn't have to go onto the blockchain. Now, at some point, A and B might want their money back, and then they can just post the current state to the blockchain and get whatever they have from their side. There's also a mechanism to resolve disputes. So this is nice because now you can start doing a transaction with someone, and you only need the blockchain once for the opening, and then you can do whatever you like, more or less. But the problem is, if you want to pay someone with whom you do not have a channel and you only want to pay them like once in a while, it doesn't pay off to open a channel. This is where payment channel networks come in. This is when you want to pay someone with whom you do not actually have a channel. What you're doing then is you forward the payment via intermediaries. And to incentivize these intermediaries to do so, you likely are paying them a very small fee. It's usually considerably lower than what you're paying to do an actual blockchain transaction, so it still pays off. So what would happen here is that A would pay B the said coins plus the small fee F, and then B would just forward the payment to C. And obviously there need to be some security guarantees on this, which state that B cannot run away with the money. We're going to talk about this a bit more later on, at least about one way to achieve this. But the key idea is that you can now connect all the existing channels into a large network, and then you can route payments from a sender to a recipient. Let's look into how this is done in Lightning. So Lightning is the key example of a Bitcoin-based payment channel network. And what they're doing is essentially each node charges a fee consisting of a base fee. This is something you always get when you forward a payment, and then a part that is proportional to the actual payment value. And every node can choose that however they want to choose it. The idea here is now that the source selects one path in the network from the source to the receiver, and it tries to take the one that is cheapest, so where it has to pay the least fees. That can be done using Dijkstra. Now, this was actually slightly simplified. Lightning considers a bit more than just the fee cost, and what exactly it considers depends on the client that you use. So there are 3 Lightning implementations, LND, Eclair, and C Lightning, and they're all slightly different. But the key idea is always try to find a cheap path using a Dijkstra or a modification. The key problem of all of the implementation is you're forwarding along one path. So if you have a large payment and you have all these channels and they have a certain capacity, remember if you only locked X coins, then you can only send X coins. So if there just aren't any paths that have this capacity and you only can choose one path, there's a lot of payments you cannot do, even if the flow that is possible in the network is larger, because you're restricted to this sending the whole payment at once. So that's obviously a problem, and that's nothing new. So there's actually is a protocol that could improve that, which is atomic multipath payments over Lightning. So what you do now is the sender splits the payment over multiple paths and sends it along the path. The problem here is still, you have the sender. The sender knows the network, but it does not know the individual balances on the links. So it does not really know which capacity does this link have that it actually selects in the path. And if one of these links fails, the complete payment fails. So along all of the path, which means that as soon as a small thing goes wrong here in the multipath payment, the complete payment fails. And failed payments are expensive, because to do a payment, every participant has to lock coins that are dedicated for that payment. And until a timeout expires, these coins become unusable. So they're locked, you cannot use them for anything. So failed payments are really annoying because you have to wait for timeouts. So one of the key issues is that you don't know the local situation, but the decision has to be made at the sender. So there are protocols that use this atomic multipath, but give a bit more information to the sender by either letting local people redecide the path or just pushing local information to the sender. However, they still have the problem if you're stuck in a dead end where the local node just doesn't have any paths, any links that have sufficient capacity on their own. The payment fails. So even if there are other links that could be combined to have the payment, intermediary nodes can no further split the payment. So this can obviously cause some trouble, and there are two key solutions how to overcome the fact that as soon as a small thing goes wrong, the complete payment starts to fail. The first one, that was a paper that was published at Financial Crypto this year, is about introducing redundancy. So if I have multiple paths and I'm not sure if all of them succeed, well, maybe just send more funds than what you actually want to pay. If you're lucky and more than what you wanted to pay arrives at the recipient, construct a smart contract that makes it clear that the sender gets the exceeding payment value back. So this is nice, and it actually works quite well. So they had this graph in the paper, which essentially says if you make a payment of 25 euro and you add what it says on the x-axis, so this u, the probability that the payment succeeds increases as is shown in the graph, which can be up to a factor 3 to 4. So that's great. But as we said before, what happens if you do the payment is that collateral needs to get locked. So you need to block something for the payment. And if you send 150 extra coins for 25, it roughly means you send 6 or 7 times what you actually want to send. It also means you lock that and make it unusable in the system for some time, which is maybe not the greatest idea, at least not to the extent that it's a factor 6. So maybe you should start off with a protocol that does not use redundancy, that is already has a high success ratio, and then you can still use redundancy, which was, for example, our protocol, but instead of a factor 6, maybe you only need a factor 1.5 or something. So it's an interesting approach, but it has this problem that you really need to lock a lot of coins into the system and you cannot use them for some time. So the second idea here is, if you locally get stuck and you do not have one of the channels locally available that can do your payment, well, most people do not only have one channel. They have multiple channels, and maybe in combining everything that is available there, you can then still complete the payment. So let's look into an example. Let's say the sender does pay this particular node. And I will do something during this talk. So we have sender and recipient. I will assume that every forwarding of a payment takes the same time. So every link has the same latency. Obviously, that's not a case in practice, but it makes the illustration much nicer because you go step by step. So it's for illustrational purposes and not to worry about what is the difference between a link having 80 milliseconds and 100 milliseconds? We will just assume that the latency is constant. So let's say we're now in the situation that the second node on the path says, well, I have enough capacity in my links, but not in one single link. Well, the protocol should work like this. It should split the payment over, for example, 2 of the links. And what happens next is that both of the nodes that have received a split payment start forwarding again. So in this example, one of them just forwards and the other splits again. Now we have another interesting case. We have 2 partial payments from the same atomic payment arriving at the same node at roughly the same time. Now, obviously, the node can forward both of them individually, but that's maybe an overhead you don't want because you need to set up 2 smart contracts. So what the protocol also has is that it will merge payments that arrive at roughly the same time. And now it can be forwarded as only one payment. And then you still have one payment part left, which arrived a bit later. So it usually does not pay off to wait for payments for a long time because you never know if there will be more partial payments. So for latency consideration, you should not merge everything, but only payments that arrive close in time. And then that's the last payment part, which will arrive at the recipient, and the receiver can then check, okay, now I got all the money, payment done. Okay, so that's essentially what we want. What are the problems in getting there? Well, the first one is, how do we do that cryptographically, in the sense, how do we make sure that none of the intermediaries run away with the money, or that the sender indeed has approved that the payment was completed? And the second aspect is the more practical one. If you have a cryptographic protocol that tells you, how can I split securely? It does not actually tell you, when should I actually do that? When does it make sense to split? And if I have multiple neighbors, how do I divide the payment value? So that's the more system-oriented, more graph theoretical aspect of the routing protocol. So that's the 2 challenges that we solved in the particular paper. And looking at the second point, you might see while sensible splitting is important, because there was this one node in the example before that was a backend. And what happened here was that the intermediary did not split over this node. So there needs to be a protocol that identifies cases when using someone in a split is just not suitable, because you will just end up in a dead end. Okay, so that are the challenges. Next I will talk about how did we solve them. But before, I was a bit vague on what are the security guarantees that we actually want. I just said something about, we want nobody to run away with the money. But obviously the paper has more formal security guarantees. I'm not going to really do the formality that is needed for the proof, because we're not doing the proof here, it takes too long, but I'm going to give you enough that they're very close to the formal statements so that you can probably see what a formal statement might look like. The first key goal that we have is atomicity. So essentially that means if S makes a payment of V coins, then this should either go through and then the receiver should get all the coins or nothing. The way we expressed it is if we have a sender S and let's say the balance is the available coins, so all the funds that it has in all the channels. And balance prime is the balance after the payment. And let's only look at one payment, not at concurrent payment. Then we're looking at a case that S lost some money, so the balance decreased. And what should happen in this particular case is that the receiver has a new balance that is at least the payment value V bigger than its original balance. So how can we do that in a slightly more formal way? Well, let's say we have an honest sender S that loses money. So we say if S loses money in this payment, then S will always have a valid receipt over a payment value of V. And if S has this valid receipt over a payment value of V, then we know that the receiver actually got a payment and that they actually gained the value V. So that's our definition for atomicity. And if S only, so what this does not say is actually how much money does S lose. So there might be different considerations here. We went for a simple one. So we disregarded fees. We said nobody takes fees. Obviously, that's not a case in practice. But the reason is once you allow intermediaries to take fees, no matter what protocol you suggest, if they take fees and if they can change the routing, then obviously there are incentives to change the way the payment is forwarded in such a way that you get more fees. And that might be, and then you have to show that the way that you design the payment incentives creates incentives that make sure that the intermediaries are still interested in maximizing the probability that the payment is successful. And honestly, we already did the cryptographic evaluation in the paper, and we did a system-based evaluation. We didn't really want to write another 10 pages on game theory, which is what we needed to do once we state we need to do fees that way. So this was one of the reasons why we completely disregarded the aspect of fees. Obviously, you can come up with something in practice. But if we don't have fees, then the amount of money the sender loses. So our atomicity definition would even work with fees. That's the part that would not work with fees. We say the sender loses at most the payment value V. So if you have fees, that should obviously be the payment value V plus a certain amount of fees. And obviously, if you're not a sender, if you're not paying anyone, you should not lose any money. So that's called balance neutrality. If you're not the sender of this particular payment, the payment should not make you lose anything. That's also kind of obvious. The last goal is correctness. Now, correctness says if you have only honest participants, so nobody drops a payment and so on, and each channel has at least a capacity corresponding to the payment value V, then our protocol guarantees that the payment succeeds. Now, okay, if you're looking at that closely, you might say that's a bit trivial. If every channel has capacity V, we can just choose the shortest path and we're done. Yes, you're completely right. The reason why this is a requirement is to exclude trivial solutions, because all the other definitions that we had before can easily be fulfilled by having a payment protocol that fails every time. So in a way, the last condition just said, we do not want trivial solutions or not strategic solutions. So that's our mandatory goals. We also had one optional goal related to privacy, which was unlinkability. So you might sometimes want that and you might not. What does it mean? Well, essentially it means, imagine you have a malicious intermediary, let's call it A. A receives two partial payments, X and Y, which have the same recipient. Then A should not be able to tell whether X and Y belong to the same payment or were a different payment. So for example, if you have this graph where S starts paying and then an honest intermediary splits, and the payment at some point, both parts end up at A, then A should not be able to differentiate that from the case when S makes two payments, both to the same recipient, and both of them at some point end up at A. So this can be a good idea if you want to have certain privacy guarantees. It also makes certain censorship attacks harder, as we argue in the paper. What it has as a disadvantage is, if you remember our initial protocol, we also talked about merging payments if they arrive at the same node. Obviously, that's no longer a property here. If you cannot tell if two partial payments belong to the same general payment, you cannot merge them. So the disadvantage is that you lose this capacity to just merge one payment and two payments into one again. But you gain certain privacy properties. So that's why it's an optional goal. Okay, good. Now that we have the goals, are there any questions before I introduce the protocol?
Can
Everyone
I ask
good?
a question about the correctness?
Yes.
So in the correctness definition, you are saying that if every honest party has capacity of V, then the protocol will work. Can you extend that definition so that every honest parties with including the splitting in total has V capacity, then the protocol should succeed as well?
I actually think we cannot. I think there are cases where you would end up in a dead end in a way. So if you have an intermediary that has, let's say, two neighbors, one gives it a path to the receiver and the other one is a dead end that only has this one link. And there is a capacity of V divided by 2 to this dead end, and in the other direction there is a capacity of the total V, then I think you would get stuck at this dead end.
No, I mean...
I'm not 100% sure, I don't think so. We tried extending it to saying that the maximal flow has to be at least V, and we could not satisfy that. So I think it's not enough for the correctness to say that if the maximal flow is at least V, our protocol can do it. So I know that it doesn't work with the maximal flow. It might work with something softer. I'm not sure.
Maybe I step in here. It all comes from the fact that you consider local routing. So as a node, you don't really know, even if you have enough capacity, you don't really know in which direction you should send it because you cannot foresee what's going to happen later on the path. So that was the problem with the maximum flow, that it might be sufficient, but you would need some global knowledge.
Yes, so I think that was the general problem, that we didn't get it to work with the maximal flow. So
won't you have the same problem of the view even if the capacities are V? I mean, you have the honest capacities. So you in the correctness stand definition, you assume that the honest party is a capacity V and there's a path from center to receiver, and the honest parties would choose the honest parties to continue with.
yeah, but you would not necessarily always choose all of the honest parties. So you might lose a path. So we might see that later in the protocol, but you only split very often if you're stuck. And it might be that then you still end up being stuck because you would have needed to split earlier. But because you didn't know what was happening later on the path, you didn't do the early splitting, and then you didn't take one of the possible paths. So I think if you do this max flow definition, you really would need global knowledge about all the balances, and that's not possible because they change too frequently. So that's my feeling about this. If you want to have an absolute optimal solution here, you need to actually know everything about the network. You could maybe do it with backtracking once you get stuck, but I don't really know how to implement backtracking in the algorithm. Anyway, maybe that becomes clearer after we discuss the actual algorithm for it. But my impression is that it would be difficult to go to a correctness definition that is better unless we're saying something that we're talking about a probability that the routing is successful. Then it might be possible, but I don't think we have any protocol with local knowledge that can guarantee that we are successful if the max flow satisfies the condition. I mean, ours doesn't. You can see that we do not necessarily find all the paths. We find like 99% of them, but not 100.
Thanks.
Okay. Okay, good. Okay, then let's move on to the protocol, starting with the part that's more on the cryptographic side. So essentially it looks like this. I'm not going to walk you through every step of this. So there are a couple of things that you need to take care of, but it looks more complicated than it actually is. So the key idea is actually very, very simple, especially if you do not want unlinkability. Once you have unlinkability, it becomes a bit more complicated, but if you don't want it, it's actually a relatively straightforward extension of what Lightning already does. Which is why I will start with a short recap. So for those of you that know payment channel networks, you probably have seen that before. Hash time-locked contracts. So what we have here is a sender and a recipient and one intermediary. So for the illustration, just going one hop. And we have a collision-resistant cryptographic hash function and an upper bound on the time to publish information on the blockchain. And then a couple of timeouts that we will use. The protocol starts by having the receiver generate a random number and then hashing it. Then it transmits the hash to the sender, and the sender starts initiating the payment. The way it does that is it sends a signed statement to the intermediary consisting of the hash, a timeout T, which is large enough that if stuff goes wrong, there can be dispute resolution on the blockchain, and the payment value V. What does this tuple say? Well, it essentially says, if you send me the pre-image of this hash H within time T, then you get the amount V. There's some verification on the intermediary side, and then the intermediary essentially forwards this. So it also says, if you give me the pre-image of the hash H within time T prime, then I give you V. And then you have to be careful how you choose the timeouts, because if one of them runs and if R completes giving the pre-image within time T prime, after that, I still needs time to essentially complete a potential conflict with S. So there has to be at least this blockchain congestion delay in between the two timeouts. So what happens now is there's a verification on the receiver side. The receiver says everything is fine, sends the pre-image, gets the respective coins, and the intermediary forwards the pre-image, and if everything works all right, gets the respective coins. So that's how Lightning does it with a two-hop protocol. And we're using something very, very similar to get the properties that we want. So the first thing we do is this initialization looks slightly different because we want to use this receipts that S can prove that it received a payment. Now the key challenge here is, when do you send a receipt? Well, actually what we're using are conditional receipts. So before the whole transfer happens, R sends a receipt over the V coins, and this receipt only becomes valid after S has paid. How does that work? Well, essentially, slightly simplified, but essentially, you do the same as in the hash time lock contract, only you add some sort of statement that says, S gave me V coins, but that's only the case if it can also present a pre-image to H. So that essentially means unless S has the necessary pre-image, this receipt is not valid. And then you have the actual payment phase, which is divided into a locking and an unlocking phase. The locking phase is essentially where everyone promises to participate in the payment. How does that work? Well, we want to have this payment example. So what happens is we have the sender starting, and the sender does the same it did in the Lightning version. It sends a timeout, it sends this H, and it sends the payment value V. And this is supposed to be signed, but I left the signing out because the slide got a bit too clustered. And then we have the intermediary that splits. Now this intermediary splits the complete payment value in two partial payment values, V1 and V2. So what it now does is it starts two partial payments with new time locks and with the partial payment values. And those are also these conditional payments that we used before. And the next node does the same. So one of them just forwards the payment with a different timeout, and the other one splits it again. And now it splits V2 into V3 and V4. Then we have this merge operation in the next step where, again, we have a new timeout and we have a payment value that is the sum of the partial payment values that are merged. And the remaining payments are just straightforward forwarding with different time locks. And in the end, the receiver got the complete payment and can check that it actually received enough coins, namely V. Now there's the question, how do you choose all of these timeouts? I'm going to skip that, not because it's essentially difficult, but it's a lot of looking into the actual protocol that you use, looking in how does the graph look like, what is the longest possible path, and how exactly do you need to add these deltas to make sure that everyone has enough time to protest. So it is important that you do that correctly to get the correctness property, but it's a lot of fiddling around. So there are a couple of things about the protocol that are more interesting to discuss, so I focus on those. And the unlocking phase is super easy as well. You just send along the pre-image as you did before. And we've proven that this actually works, and it's super simple. Now, we also might want to have unlinkability. So that's where the more interesting cryptographic aspects come in. The problem with the protocol before is everyone sees the same H and everyone sees the same X. Not so great because it's linkable. So you want to have different HIs, and they should not be easily linkable instead of the H. So how do you get those? You need a bit more. You need a bit of additive homomorphic functions. So instead of using a normal hash function H, we now use an additive homomorphic one. What does that mean? Well, it simply means if I have two values, if I hash each of them and then add the two hash values, that's the same as if I would have taken the values first, added them, and then the hash. And we also have an additive homomorphic public key encryption scheme. So what's the key idea of what we're doing for unlinkability? Well, whenever you forward a payment, for each of the different splits that you create, you add some randomness to the H value that you have to create the new one that you're forwarding. And to later give the recipient the possibility to get rid of that randomness again, you're encrypting the randomness, you're adding it to the already existing randomness, and the encryption is under the public key of the receiver. So only the receiver can decrypt the sum of all the randomnesses. If it arrives at the receiver, you essentially just get rid of the randomness by decrypting it and adding it in. And then on the way back, you have to be careful that everyone is now expecting a pre-image for their own private HI, not for the general H. So you have to add the randomness back in. And that, if you look at the numbers carefully and do a couple of tricks with the domain and codomain, you will see that this perfectly works out. For the moment, just believe me on that. You can go over it later if you don't. There's a proof. What you might be wondering if you see this protocol, this might be nice and it doesn't even look that complicated, but it says additive homomorphic and other nice stuff. And up to now, we were fully Bitcoin compatible. It all was easy and worked with Bitcoin, and this looks complicated. So are we losing the fact that we can do that over Bitcoin? We actually do not. So if you don't remember the remaining part of the protocol, at least remember this. It all stays fully Bitcoin compatible if we instantiate it using adapter signatures. So this can be used in Lightning, even with the unlinkability. And that's all I want to say about, or all I have to say about the cryptographic protocol. Are there questions? It's not very formal what I did, so, and it's certainly not a proof, so. Okay, good. Then we move to the second and last part, which is, now that you know how to actually do that using hash functions and additive homomorphism, if you want unlinkability, that's nice, but how does a node decide when to split, if to split, and which of the neighbors gets what amount of coins? So we divided this routing decision in two parts, using a couple of assumptions. The first assumption, so it's pretty standard, saying that you know the complete graph, but you do not know the local balances. So you don't know how many funds there are in each direction, which is the same with all the existing protocols. We said that the receiver will be known, or at least some way that you know the direction you have to go. So you're losing some sort of, you don't have anonymity in this protocol. You can maybe get some amount of it by doing some changes here, but by default, you don't have anonymity. And then the routing protocol at each node will do two things. It will first get a candidate set. So it will look at its neighbors, and it will choose a set that says this neighbor might be suitable for splitting. And suitable for splitting means that after some metric, it's closer to the receiver than the current node. And we'll talk about possibilities to define closer in a minute. And what will also be in the set is some sort of distance to the recipient, which can then be used to choose nodes that are particularly close, to have short path. And in the second step, you then decide, split the payment that I got, which might already have been split before. Take the payment value and then split it over this candidate node set. So since we talked about splitting quite a lot and about distances and being closer a bit less, I will start with the second point. So how can you split? The first approach is easy. You just don't split. So this is the one we use to compare to what happens if you do not have our splitting functionality. So you just choose one node in this candidate set C, so that the channel has at least the available funds. If you have multiple ones, you choose the one that is closest to the receiver because that gives you probably the shortest path. So in this particular example where we want to route 6 coins and we have 2 neighbors with 2 and 5, the whole thing fails because you cannot split. Now let's look into something more interesting. How can we split if we want to? Well, we can say we want to try to get as close to the recipient as possible. So we start by looking at the node I in our candidate set C that has the least distance to the receiver. If we have multiple nodes, we break the ties randomly. And then we look at its funds Fi. We then assign as much as possible to this node I. So if the capacity of this node is sufficient to do the full payment, it does the full payment. If not, it does the maximum that can be done. And if you're not done, you now continue. You look at the node that is the next closest and assign the remaining value there until you either run out of neighbors or you assign the complete payment value. So what would happen in this particular example is that we first have this node. It has a distance of 2 to the receiver, so it's the better one, the closer one. So you assign 2 because that's the maximum you can assign. And then you still have the other node and it has to get the remaining 4 because there's no other node left. So that's one way to split, but it might be bad if all of the nodes that are very close to the recipient only have a very low balance, then you need to split a lot. And if you need to split a lot, then things might go wrong. You could also say we attempt to split as little as possible. Then the idea is do not split if you can prevent it. If you can't prevent it, you do the same as you did on the slide before, but instead of prioritizing by the distance, you prioritize by whom can I send the most? Because then I might probably have to split least. So in this case, that would mean you first start with the node that has 5 in terms of funds, because there you can get rid of most of it, but you can't do the full 6, so you're giving 1 to the remaining node. So in this example, you had to always use both of the nodes, but there might be cases where you can get around with using less. And the last approach we tried was just for comparison, splitting randomly, but making sure that we did not send more than was possible to send. So that's one part of the routing protocol. And there's also the question, how do you get C? I think I'm close to running out of time, right?
Yeah, I mean, we typically end on the hour to respect the speaker's time. If you go long, that's okay. Some folks might have to duck out, but you're welcome to keep going.
Okay, so I'll make this short. But the key idea is at some point I'm supposed to explain what interdimensionally means, and I haven't done that yet, which is where we get in now. So we looked at 2 protocols on how to define this closer. So the first one is simple. You look at the graph and you look, whoever has a shortest path to the receiver than you, is closer. The distance is the shortest path length. That's simple, but it has one problem. Very often there's not a lot of nodes that really have shortest path to the receiver. So in this particular example, you ended up with only having one possible path. And then you can't split. So the whole protocol is maybe not that suitable for splitting because it doesn't have a high flexibility. What we did instead was we used an approach that has been done in Speedy Murmurs, which is a different routing algorithm. We built spanning trees, and any neighbor if you have a shorter path in one of those spanning trees, you know that there is a path via this neighbor. It might not be a shortest path in the whole graph because a spanning tree removes certain links, but you know that there is one path. It might not be short, but it's there. So that's a potential candidate to split over. And then you can just take the minimum of all the tree distances as the distance that you mainly look at. And this is where the interdimensional comes in. Original Speedy Murmurs also used multiple trees, but it would treat them independently. So you would in the beginning decide, this is the tree that I use, and then you would ignore the remaining ones. While this one considers all the trees at the same time. So it has multiple dimensions being made up by this distance measures. All right, so this is one, and because that was a bit abstract, there's an example here. Imagine you have those two spanning trees. Doesn't matter where you got them from, we just have them. What the sender now does is it checks its neighbors, and the gray line indicates any link that can be used by the routing protocol. So the first one can be used because this node is closer in the first spanning tree. The second one can be used because the node is closer in the second tree. Now, this case is interesting because this can be used as the neighboring node is closer in the second spanning tree. It only has a distance of 2 in the second spanning tree, while the node itself has a distance of 3. Now note that the second spanning tree doesn't contain that link, but that doesn't matter. That's not our metric. It just says it has to be closer in the spanning tree, not it has to be connected to me in the spanning tree. And then this one is clear because it's in the tree, that one as well, that is clear. And this is the same as the case before. You don't have a direct link in any of the trees, but the node is clearly closer to the recipient in spanning tree 1, so it's included. And clearly you can use the last link. So what that illustrates is, if you compare it to the distance before, is that you have a lot of flexibility in choosing the path if you use this, but at the same time, you can exclude these dead ends in this particular example. So you know that the cases where there simply is no path. So that's why interdimensional Speedy Murmurs gives you a lot of options. And to show that, we did a lot of simulations. And I'm going to be really short on that one because we did a lot of configuration, extended the existing simulator, and the code is available. Normally that's the time where you have like 1 or 2 slides on why we run the different parameter settings, but I always find that a bit boring and you can read it up in the paper. So I'm just going to give you the nice figures. So this one essentially says we used Lightning data, but Lightning doesn't have transactions. So we said we're assuming that we have exponentially distributed transactions for this one with a medium transaction, with an expected transaction value of roughly €50. And the average capacity in a link in Lightning is 200. So it's roughly a fourth of the value. What you can see here is you have the trees on the x-axis, so the number of spanning trees. And these parallel lines are the hop distance. So that's the one where you simply look for the shortest path. And you see, because there's really not much of a difference between the different algorithms, as there's not a lot of paths available. While interdimensional Speedy Murmurs performs a lot better. You still don't see much of a difference between the different splitting, apart from that random splitting doesn't work, but that's simply because the algorithm is already so close to 100%. If we're in a situation where we make larger payments, so high expected values, we can see that splitting really helps. So this orange line on the top is if you split and always try to get as close as possible to the recipient, while the red line is the one without splitting. So you gain a couple of percent, and you gain already a lot by using interdimensional Speedy Murmurs, which by default, even without splitting, is quite flexible to route around situations. And this slide just says that our results are consistent if you use something different than exponentially distributed values. If you use different topologies than the Lightning topology, it's still the case that this orange line that is splitting is consistently the best. If you vary the expected transaction value, as long as the value is big enough that splitting makes sense, splitting really small payments isn't really sensible, you get an improvement. The one thing that's not really the case is if you have dynamics in the network, because a lot of the edges deplete, but that's not specifically a splitting issue, we believe, that just needs some rebalancing either on-chain or by routing in circuits, and we didn't do that, so we think these results only make sense if you really look into rebalancing and a bit more realistic dynamics. So, but that's one aspect for future work. So that's essentially all of our results. I want to lose one sentence about a protocol called EFNA, because it also does splitting. The key differences are that this protocol is mainly non-atomic, so they don't guarantee, so there might be partially succeeding payments. That's what they targeted on. There is an atomic version, but it doesn't work over Bitcoin, and it's just a cryptographic construction. So they didn't do the whole aspect, how do you actually integrate it into the routing? So that's the difference between the two papers that were written roughly in parallel. And yeah, that's it. That's my last slide. If you want to read the preprint, that's the link.
That's great. Thank you so much. Let's go ahead and open it up for questions. We are recording, so if you don't want to be in the recording but still have a question, feel free to type it in the chat and I'll read it out for you. But otherwise, go ahead and jump right in.
Hello, my name is Yanis. I have this one question for now. Is your algorithm dependent or influenced by the number of hops between the sender and the receiver? Because my thinking is that the more hops that a payment has to go through, the more the chances that there is going to be the weak link in between that will not have enough funds. So
you're right. That's the same for all of the protocols we looked in, not only ours.
Absolutely.
The higher the distance, the more likely it is that something goes wrong. I cannot give you exact numbers. We didn't actually look at it, but you're completely right that if you have a high distance, there's more of a possibility to go wrong. I think we're still, well, I don't have concrete data, so I don't want to make a statement on it. My assumption would be that we're still better than other algorithms with that, so it doesn't degenerate that badly, because a higher distance usually also means that there are more paths between the two. if you are at a very short distance, there's only a small number of short paths. So it might be that this function that we have that says something is closer doesn't give us a lot of results. And then there's not a high degree of flexibility. While if we have a lot of options, if we have more paths available, our routing algorithm tries to route around it locally. So if there's a problem, we have some flexibility on how to solve it. So what I would expect, but I only have anecdotal evidence of this and nothing that's statistically significant, is that our algorithm, like all the other algorithms, decreases in performance when the distance between the two increases, but the decrease is much less in comparison to other algorithms.
Cool. Okay, thank you.
Anyone else? Going once? Twice?
Actually, I would love to ask the unlinkability arises from, or it seems to improve censorship resistance because you can kind of effectively shield a mount somewhat to intermediaries. Is that correct?
Actually, I excluded this discussion, but it's a longer one in the paper. The key idea with the censorship is if you have a rational intermediary and you try to maximize your gain, and you're seeing two payments, both, well, you're forwarding one coin each time. One payment is an atomic payment of one coin, and one was the largest payment that was split, and you only get one remaining coin. So what is happening here is that if you're only forwarding the payment that was one coin from the beginning, then that's more likely to be successful than your split payment. Because for the split payment, also the other 9 coins have to somehow make it to the recipient. So from a sender's perspective, the fact that the intermediary split increase the probability that it succeeds. But from intermediary perspective, a payment that has been split before it reaches you is less likely to succeed than a payment that has not been split before, if it's the same value, because only for a payment that has not been split, only your part has to succeed. For another payment, all the parts. So that might lead to the case that if you know a payment was split, you might decide to just, if you don't have a lot of capacity, to just drop all of those, which would lead to the fact that the whole thing we try to gain by splitting in terms of like the total success ratio being higher no longer works because all the split payments are dropped. So in the paper, there is an evaluation how that affects the splitting. And if a lot of parties do that, you can indeed see that depending on how exactly we split, our success ratio might fall below what we got before we started to split, which is not really what we want. So that's one of the key motivations for unlinkability, because you can run this specific attacks where you sort out split payments.
It seems like it would depend on some, well, I guess my original intuition for this problem would be that payment size would be somewhat scale invariant. And so you'd have less visibility into that, but I guess there's some reference level of the average size of the channels that are active. Yeah,
so what it depends on is, essentially the simulation show that you only need splitting if you have like a rather, well, not a large average payment, but if the ratio between what you have in capacity and what you have in payment is rather high. So like at least 25%. But if you look at Lightning, then each channel has like, I don't know, 200 euro or a bit more, $250, I think were the latest numbers. So if you do something around doing your, like, a larger grocery shopping trip, then it would be the type of payment size where it starts being really interested in that you can split it.
Awesome. And then one other question I had, if you were going to do the game theoretic evaluation, what assumptions do you feel would be probably sufficient to come up with a conclusion that rational actors will lead to like consistent settlement, right?
It's actually quite difficult, because you essentially would need to tell an intermediary that the probability that a payment fails if they do something that doesn't agree with the incentive is so high that the expected gain from it is lower than if they just follow the protocol. And that's really complicated, because the probability of a payment to be successful is dependent on the topology and on the number of concurrent payments, which leads to situations that can be suboptimal. So I'm not sure if we can show that. What could be possible is that a node can decide for each payment individually how much. So the sender sets a maximal amount of fees, and then the nodes can decide how much they actually take for this specific payment. And the advantage of this is at least that it doesn't make sense in this case to reroute the payment via some other people that then are controlled by you and then decrease the probability of success, because you can just say, okay, I'm taking more, rather than rerouting. And it at least has the advantage then that you would not actually endanger the success of the payment by trying to tinker with the routing algorithm. You would just see, okay, in this case, I can probably take 4 times of what normally takes, so I take the 4 times. That might be, at least with regard to success ratio, a good idea. And if the sender says, hey, I'm willing to pay that, then, and as the intermediary, you still have to hope that the next node does not do the same and then uses up all the potential fees. So I think there is something you can do by just saying, take whatever you want of the fees, but be aware if you take too much, then there's nothing left for the next one, and the payment will fail, and then you won't get your fees anyway. So, but it's really complicated to put that into a game theoretic approach, because you don't know what exactly the topology looks like.
Yeah, I imagine a repeated game assumption would really help.
Yeah.
Very reasonable. Thank you.
Okay, so I had said one more question in the chat, but I'm going to change my mind on that, and we're just going to call it here. Thank you so much for your time and this amazing presentation. Really appreciate having you out to give us this talk. And for those of you watching, we also have another talk coming up on Thursday about modular politics, about online governance for online communities. So feel free to join for that. It's 1 hour later, start time, same Zoom link. But again, Stefanie, thank you so much.
Thanks for the invitation, guys.